Today, to finish up your notes for this chapter, we are going to talk a little bit more about pressure and buoyancy. So to start out, I'm just going to use the pressure of water on a body, but realize that any fluid can use the same formula or concept. You'll simply be given a different density. So, letter A, pressure in a fluid is the same in all directions. The pressure of water on a body or any fluid depends on the density of the fluid, the depth, how far down underneath the surface your object is, and gravity, 9.8 meters per second squared. For our formula, if we have the pressure of water on a body, you would, instead of doing force over an area, because there's not a solid thing that you can hit, we're looking at this fluidly and it's underneath a surface. You would simply take the density, which is this Greek letter rho, it's like a curvy P, multiply that by the acceleration due to gravity, and then times the depth. The depth is really similar to a height. We're just below a reference point this time. And pressure will still be measured in pascals. And then I hope you remember from seeing the bases in class that the shape of a container has no effect on the pressure. That's a question that'll be on your test. Let's imagine that we have something underwater. So I've submerged an object underneath the surface of a fluid. Well, if it's going to be a buoyant object, which means it's going to try to float a little bit, that means the fluid exerts a greater upward force on the bottom of the immersed object than it does a downward force on the top. So as you can see, I drew the magnitude or the size of the force coming from the bottom of the object as larger than the ones pushing down on it from the top. So the top of the object is a certain height, and then we also have the length of that box to add to it. So the bottom of the box is actually deeper under the surface than the top is. Now these side-to-side arrows represent the pressure. Okay. Notice that from side to side, they're the same size, but as we go deeper underneath the surface, that pressure is growing. So the further you are underneath the surface of a fluid, the more pressure there's going to be. But if we look at this idea of the greater upward force on the bottom of an object as opposed to a smaller downward force, this is what tells us about buoyancy. So the definition for our buoyant force is the net upward force exerted on an object immersed in a fluid. Hopefully you remember out of the three principles, Archimedes, Bernoulli, and Pascal, Archimedes was the one that had to do with buoyancy. And in 212 BC, Archimedes discovered the relationship between the buoyant force and the weight of the fluid that gets displaced by an object. So far, we just talked about that conceptually. Remember the beach ball and trying to push it underwater? How it was really difficult to do because it displaced a lot of water because there's a big volume. So that resulted in a large buoyant force. Well, mathematically, we can actually come up with a relationship on how to calculate that buoyant force. I use the word buoyant as a subscript. You can make that a little bit shorter if you just want to do F with the subscript of a B, so you don't have to write out that word if you don't want to. But to calculate the buoyant force of something, we would look at the density of our fluid times the volume of the object, and then times our acceleration due to gravity, which is 9.8. The buoyant force is still going to be measured in newtons, just like all of our other forces have been so far this year. Now, in your notes, you should have what each of these variables are equal to. I do want you to scratch out where it says for water and for air, just scratch out the for air part. Okay. So the density of water is considered to be 1,000 kilograms per meters cubed. So it's mass over volume. The air density is going to be a little bit different, and I'll give that number to you when the time comes. For volume of your object, if you have something that is kind of rectangular in shape, you would do length times width times height. If it's a sphere, we'll talk about how to calculate the volume when the time comes. And then remember that gravity is 9.8 meters per second squared. Now, to look at whether an object will sink or float, an object will float if its density is less than the density of the fluid that it's submerged in, and it'll sink if its density is more than the density of that fluid. And all objects immersed in a liquid, even the ones that sink, have an apparent weight that's less than when the object is in air. So I don't know if you've ever tried to pick up somebody while you're in a swimming pool. They feel a lot lighter than they would in air on the side of the pool. That's what this is talking about. And that apparent weight, how much they feel like they weigh, is going to be the difference between the object's actual weight and the buoyant force. So we can write that as a mathematical formula. You can calculate the apparent weight of something, and again, I wrote out the words as subscripts. You can abbreviate those if you'd like, but to find the apparent weight of something, we would take the object's actual weight and subtract the buoyant force. And then I put a little note here for you. Fg is the object's weight, so remember, if you're given the mass, you would need to convert, and you do that by mass times gravity to get the weight. And then you can find the buoyant force with the formula from up above. You should be subtracting a weight and a buoyant force that are both in newtons, which will give your apparent weight units of newtons as well. That's it for this chapter. It is really, really short. We are going to cover a lot of demonstrations and labs in class, so I hope that you've been able to see them. If you were absent, make sure that you ask me about them because I really want you to get that hands-on feel for some of the concepts in our notes. Thank you and have a great day.